All right, today we are looking at lesson 63, and it is our final method for solving systems of equations. So we need to remind ourselves that the solution of a system of linear equations is a point, right? It's an ordered pair. We could also call it a point, okay? Not a pair of points, just one point. Okay. It's a pair of coordinates. It's an x and y coordinate. All right? So the solution of a system of linear equations is a point. Now, more specifically, this point represents where the two lines intersect. Okay? It is the intersection point of the system of equations, the two linear equations. Now, or two or more. We could also, because it is the point of intersection, one of the methods that we use to solve up to this point is solving by graphing. So you can actually sketch the graph of the two lines, find the point of intersection, and that point of intersection is the solution to the system. And we did that by hand, and we also did it using the graphing calculator. Okay, and we'll go over that protocol on or syntax on tomorrow when we review for the Unit 6 test. Now, we also solved the systems of equations by substitution. Substitution is where you solve one of the equations for one of the variables, substitute that expression into the other equation, and then solve for the variable and substitute it back in to solve for the other variable. So the substitution is part of every method except for graphing. Substitution is an important concept. All right, and then today we will learn how to solve systems of equations by elimination. All right, and this is it. This is I say this is it. There are some matrix techniques that you'll learn in Algebra 2, some matrices, methods for solving systems of equations, but they are based on these methods anyway, except for Kramer's rule. Kramer's rule is a little bit off the beaten path. But you don't even know what Kramer's rule is, or who he is for that matter. Kramer, the dude from Seinfeld, he is a mathematician. Came up with some really advanced methods for solving systems of equations. It's not him at all. It's a different Kramer, but today we're going to look at elimination. Now, here is elimination. The goal of elimination is to get opposite coefficients and eliminate one of the variables by adding the two equations together. Okay, that's our goal. So, in solve by graphing, what do? We graph. Solving by substitution, what do? Substitute. Solving by elimination, what do? We eliminate, right? So all three of these methods are very descriptive. You want to eliminate one of the variables by getting opposite coefficients and adding the two equations together. And this is going to make really good sense when you actually do it.
Is it hard?
No, this is, I think, is the easiest method. As long as you remember the processes.
I don't remember how to
Yeah, putting the process into words always makes it complicated, right? Like substitution. Solve one of the equations for one of the variables. Substitute this expression into the other equation and solve for the single variable that's left. Take that value and substitute it into the other equation to find the other variable that you didn't solve for the first time. But it's important to be able to at some point verbalize it, because if you can verbalize it, then you can do it, right? All right. So the goal of elimination is to get the opposite coefficients. What do you mean by opposite coefficients? Give me an example.
I don't know.
You were about to say?
5
and negative 5, right?
Yeah, that's what I was thinking. But then my mind said
2 and negative 2, negative 12 and positive 12, because those have a sum of 0. If you add a number and it's opposite, you can eliminate one of the variables. So, for example, we have 5x plus 2y equals 9, negative 5x plus 6y equals 7. Our goal in the elimination method is to eliminate one of the variables by getting opposite coefficients, right? We got it. Positive 5 negative 5.
So what do we do then?
All right, what did the process say?
The goal of elimination is to get opposite coefficients and eliminate one of the variables by adding equations.
Add the two equations together. 5x plus negative 5x.
Oh,
No more x.
Cool.
2y plus 6y is 8y. 9 plus 7 is 16. So y has to equal 2. All right. Now, y equals 2. To find x, we would substitute that value into one of the original equations. Let's use this one.
So 4.
That's 4, so subtract 4 from both sides.
So x is gonna be 1.
5x equals 5, which means x equals, it's 1. Yes, and then 1, 2 is going to be our solution. Okay? Now, it would make sense to, because we just got 1, 2 from using the first equation, check this into the other equation. Is negative 5 times 1 plus 6 times 2 equal to 7?
Yes.
That's negative 5 plus 12, right? Negative 5 plus 12 is equal to 7. So we're going to take this. This is a solution to that system of linear equations. So that's what the elimination method looks like. Now, let me ask you a question. We just randomly added two equations together.
Pretty much.
Why are we allowed to do that?
Because the elimination. Because the coefficients are
Right, because we have to know what we're allowed to do to things. And that's one of the big math questions. What am I allowed to do to this? How do we know we're allowed to add these two equations together and that the result of adding those two equations together is going to somehow still give us the solution to...
Because the coefficients are opposite.
Yeah, but how do we know we can add those two equations together? Can we add any two equations together we want to and still get an equivalent equation?
So it has to be
what's it called? Opposite coefficient.
I correct that.
No, opposite coefficients is going to allow us to eliminate. Okay, but if we just had two equations, just two random equations, are we allowed to add them together?
No.
Well, let's see. Let's just take two very... Give me an equation that's always true.
A squared plus b squared equals c squared.
That's not always true.
Theorem.
It's not always true. That depends on A, B, and C being the sides of a right triangle. Here's an equation that's always true. You ready?
Yes.
Equals 7.
There you go. Always true.
Oh.
That's an equation, right?
Uh-huh.
Here's another equation.
10 equals 10.
What happens if you add those two together?
17 equals 17.
Because we're adding equivalent values to both sides of the equation, right? So if we're saying that this is equal to this, then it's okay to add that to both sides of the other equation, right? So the rules of solving equations say that we are allowed to add the same thing to both sides. Well, if this is the same as this, then we're allowed to add it to both sides of this equation. All right? So I just want you to kind of intuitively know why you're allowed to do that. You may forget that, but it's an important thing to remember. All right, so easy process when you have opposites. It's not uncommon to have opposite coefficients in an equation. We've seen equations like that before. What if you don't have opposite values given? If you don't have opposite values given, because we're dealing with equations here, what are we allowed to do to equations? You can multiply, divide, add, or something. So all the rules of things that we're going to be allowed to do, we're allowed to change all the signs in any equation. That's the same as multiplying everything by -1, right? But a lot of times all you have to do is change a sign to get opposite coefficients. If you had 5x and 5x, then if you change all the signs in one of the equations, then you'd have 5x and -5x. So that would work, right? All right, we're allowed to multiply one equation to get opposites. It's the same thing, right? Yeah, same thing as the previous one. I just wanted to be aware that sometimes you can just change all the signs. I'd rather you think of it that way than multiplying by negative 1.
I have to write that down because I think it's going to confuse me.
What?
The multiplying one equation together.
No, it's not. It's completely different from the first one.
Oh, it is?
The first one is specific. The second one is, general. Changing all the signs in any equation is equivalent to multiplying everything by negative 1. It's just it's a little trick, right? It could have followed number 2. This is but we can also multiply both equations to get opposites, right? Sometimes we'll have to. This is the things that you'll have to do to get opposites here. Excuse me. We are also allowed to, because in the elimination method we need our x and y's to line up. We're allowed to move things around by rearranging the equations to line up like terms. And we do that by adding or subtracting things from both sides to get things in the same position. I need to write this. Good. All right. So just kind of keep in mind, those are the things that you'll have to do, periodically do to get opposite coefficients. And again, our goal is to get opposite coefficients so we can add the two equations together and eliminate one of the variables. Okay, so let's look at a few more examples. You ready? Next one. 7x plus 3y equals -5. Now, I kind of want to encourage you. The way this is written, if you're writing these on your paper, always write them on the left-hand side because the workflow is going to take us to the right. I'll show you how I want you to write them in just a second. Write these on the left-hand margin of your paper. Don't try to do these problems side by side and need to do them one over top of each other. Okay. Do we have opposites here?
Yes. But they're the
Opposite coefficients. We don't have any opposite coefficients. What's the easiest way to get opposite coefficients? Change all the signs in one of the equations. All right, let's change the signs in the second equation. Let's make that -2x, -3y, and -5, which is the same thing as doing what? We just multiplied by -1, right? 7x minus 2x then gives us 5x. 3y minus 3y is 0. -5 minus 5 is -10. Divide both sides by 5 and we get x equals -2. And we know we're not finished because the solution to a system of equations is a point. It's an ordered pair, right? So we need to find the y value that accompanies that, and we're going to find that by substituting x equals -2 into one of the original equations. Let's just use the first one. Might have been easier to use the second one, but we'll just use the first one. We substitute -2 in for x in the first equation. We get -14 plus 3y equals -5. So I want to add 14 to both sides. That gives us 3y equals 9 and y equals 3. So my solution is -2, +3. Since I used the first equation to get -2, +3, it's a good idea to go back to the original second equation and check it, make sure that works. Is 2 times -2 plus 3 times 3 equal to 5? It is. So we will take that as a good solution. Checked. Okay. All right. Not bad, right? So that's kind of an example where we can do this. What about this one? Now we do have two linear equations here, not necessarily in any form though. The second one is in standard form. The first equation is not in any of the forms that we're used to working with. It's not in any of the forms of a linear equation. So this is one of those where I was telling you, it's kind of good to take this equation and write it on the left side of your paper. Oopsie, I don't have any idea what just happened. 5y equals 8x minus 2, and 4x minus 3y equals negative 2. Sorry, I've got, I was actually sick over the weather delay. I probably would have missed a couple days, so it saved me some money. Money, 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 money. All right. Now, we can't, if we try to add these together now,
That would not work.
the x's aren't on the same side, right? So they wouldn't eliminate, we wouldn't get, so it's kind of a good idea to change these two equations, or one of the two equations, so that they line up. You want to change the top equation? And the reason that I say, if you write it over here to the left, then you can just kind of go right over here and say this is negative 8x plus 5y equals negative 2, and then 4x plus 3y equals negative 2. Now we kind of have both. Did I copy? I copied something right. Yeah, minus 3y. Sorry.
But you don't have opposite coefficients.
We don't. So we still have to do something to be able to get these two to eliminate. Right? Yes? Hello? Hello? All right. So then what do we have to do here? If we want to make opposites, what can we do?
You can multiply the bottom equation by 2.
We can multiply the bottom equation by 2, right? And so that will, if I multiply this by 2, and I don't have room, but if you had room, you could kind of just keep writing things over to the right. Yeah, so we could go over there. And you could have negative 8x plus 5y equals negative 2. And the bottom equation is now going to be positive 8x minus 6y equals negative 4.
Okay, that's stupid.
Now we have opposite coefficients. Do what?
You write it down now instead of writing it right?
Yes.
Okay. Keep going to the end.
And then we will have negative 8x plus 8x. Miss Johnson, right there on that desk. Just grab one of those. Not a problem. No. Oh, it's okay. All right. Then we can eliminate the x's, and that'll leave us with negative 1y equals negative 6. Divide both sides by negative 1, and we get y equals positive 6. So now that we know the y coordinate, what do we do with that?
You plug it in.
Substitute it into one of your original equations. And the second one is easier, I agree. So if we use the second equation here, we would have 4x minus 3 times y equals negative 2. That's negative 18, so add 18 to both sides. We get 4x equals 16, x equals 4. You can plug that in to make sure that it works. And it does. So 4, 6 is the solution to this system of equations. Okay? All right? So elimination, sometimes you have to move things around to get your terms lined up, and you can multiply to get opposites. All right? And then one other example we'll look at is this one. To solve the system by elimination. If we're solving a system of linear equations, we're looking for the point of intersection. Remember that, okay? And this one, 4x minus 3y equals 15. Let me rewrite this over here so we can. 4x minus 3y equals 15. 6x plus 5y equals negative 25.
This is complicated.
Nah. No, you can multiply both equations, but we can't multiply them by the same number. Yeah, absolutely. You can multiply any equation by anything you want to, except for 0.
Use
You wanna make 12 and negative 12?
Yeah.
All right, so you want to eliminate x then. Yeah. So if we eliminate x, you can eliminate y if you like. We would multiply the top by 3 and the bottom by negative 2, right? And then that will give us 12x minus 9y equals 45. And negative 12x minus 10y equals 50. Big numbers. But that's okay. We have opposite coefficients now, so we're ready to eliminate. So, elimination. Do whatever's legal to get opposite coefficients so you can add the two equations together and eliminate. 12x minus 12x, no mas x, right? Negative 9 minus 10 is negative 19y. 45 plus 50 is 95. Divide both sides by negative 19, and that gives us y equals negative 5. Is that right?
Sure. Yeah. I think so. Yeah.
Yeah, because 5 times 20 is 100. So 5 times 19 is 95.
Oh, I thought of a different one.
All right, y equals negative 5. Then we'll use one of our original equations to make that substitution. Just take it doesn't matter which one. Let's use the first one. 4x minus 3 times y equals 15. That's positive 15, right? So we want to subtract 15 from both sides. That's going to give us 4x equals 0. Divide by 4, x equals 0. So 0, negative 5 is our solution. That's a y-intercept, right? So if we put both of those in slope-intercept form, we might have seen the common point of intersection there.
Is that the last example?
Pardon?
Is that the last example?
There's a word problem we're going to skip, but yes. Okay?
Lovely.
There's your homework.